Start now. Okay, so good afternoon, everyone. So let's for this afternoon session, we have two speakers, Professor Rajeev from ISI Bangalore and Imran Biswas from TFR Camp. Professor Rajeev will be working on stochastic models for barrier crossing and fluctuations in local time scale. Please.
Oh, how do I have to put this? Yeah, okay. All right. Thanks to the organizers for the invitation to give the talk. I think there's the only talk that's not aligned with the title of the symposium, maybe a little off. But still, it is a applications-oriented talk. Non-aligned country. Okay. So this is a joint work with Vijay Ganesh, the student doing his PhD at Cambridge. He was a intern, student intern. He interned with me for some time, and during that time we got talking, and and then he brought in some chemistry problems. So an alternative title for this talk could be modeling chemical reactions as a stochastic process. Okay, so again, I was planning to present it, but some outside events disrupted my plans, and so I have to use the black chalk, green board. So first is the conceptualization. Of the problem, and then mathematical Okay, I think they can hear. Okay. It's oh, for those people it is okay, I think. Yeah. Yeah, okay. Okay, so mathematical model, then a singular stochastic differential equation. And for computing reaction rates. Okay. So this will be the bare presentation of the results, explanation of the problem and setup, etc. And then if there's time left, we'll go into details of proofs and things like that. So conceptualization. So this is basically about how modeling how a chemical reaction takes place. Okay. And your state space. So you're basically tracking the trajectory of a molecule, let us say. And the state, this is described by certain coordinate systems. Okay. And you have the state space. And in that state space, there are two regions. So state space. And you have, so it's a multi-dimensional space, you know. And these are the reactants, a region called the reactant region. And the particle starts from there and crosses over into a region called the product region. So there are reactions taking place and you get a product. But in the state space, there are two regions separated. And in this separate, in the in-between region, here, there's a potential barrier. And so the particle has to cross this barrier. Okay. A physicist called Kramers, not the statistician, but a physicist. So he introduced a stochastic model for this sort of crossing, okay, by adding a Brownian term, okay, and proposed that the crossing happened because of thermal fluctuations, and he modeled that by adding a Brownian term, okay. So that was a diffusion model. Okay. And then people started studying the actual crossover process. Okay. And this was sort of described by what is called a transition path theory. So transition path theory. Van den Eingen. He's a mathematician at Courant Institute, I think. So they had this model for how the transitions actually happen. Okay. And they try to model it by a separate process, separate from the diffusion XT. What they were interested in is something called the reaction rate. How fast the reactions happen. And that depends on the number of crossovers, okay, the barrier crossings from R to P. Okay. So you had something starting here, and then it would go here, fluctuate across the boundary, okay, going in and out. After doing this for some time, it eventually jumps across into the product region. This portion, that is the from which the particle never returns back. So the last time it was in the region R. From that point onwards, until it hits P, that portion is called the reactive trajectory. That's this portion. And what they're interested in is the number kappa reaction rate, which is defined as the number of reactive trajectories, that is the number of times it goes across in times 0 to t. Okay. Where NT, capital NT, is the number of reactive trajectories during 0 to t. So this is number of crossovers. So this is basically the framework, the modeling framework, if you wish. Okay. Basically, it's a multi-dimensional problem. So these regions are all in some high-dimensional space, and but for certain systems, using appropriate coordinates, okay, and if you take a section of the potential energy surface, then the problem becomes one-dimensional. Okay. If you look at the potential energy surface, then it can consist of various, in this region, in this in-between region, it can consist of various, it can be complicated. But the example that we are going to consider has a single barrier. Okay, that's what I'm saying. When you take a one-dimensional section in certain physical systems, then you get a nice barrier. I think something that involves the ammonia molecule or something. Okay. So my Vijay may be able to explain that. I think he's there somewhere in the cloud. All right, so let's write down the stochastic differential equation. So it's dxt pxt dt plus sigma dbt. Okay, and of course x0 is equal to x. This function b is the derivative of a potential, so del u by del x. So b is equal to and u is the potential that we are talking of. And in this particular example, so all this can be done more generally, so I'm not going into that. We'll deal with a specific u. There's some constant here. Okay. Coming from chemistry and all that. Ux. So the picture is like this. It's a double well potential. Okay. And this point is A and this point is B. And for us, B is actually equal to minus A. And this point is 0. So you have this interval AB. And the point 0 is inside. Okay. So 0 belongs to AB, and B is actually minus A. And in this part, it's what is called a, there's an explicit expression for this. Lambda x power 4 minus, wait a minute, let me check. It's square x power 4. It's square x power 4 minus half lambda square x square for x in AB. So this is the part really that matters. Okay. A minus infinity to A, that's the reactant region. And B to infinity, minus infinity to A, and B to infinity. So this is the reactant region, this is the product region. And the particle is trying to cross over from A to B. And in between, from A to B, the potential is like this. And beyond this, we can choose what we want. Okay. It's not relevant to the reaction. And we choose the functions so that this is equal to K mod X plus some L. So these two parts from here onwards, for X slightly less than A and slightly bigger than B, symmetric, okay, are like mod X. K times mod X plus L. For mod X, let me just write it as mod X going to infinity. Okay, but basically it's mod X below A and above B. The reason why we choose this is that we want this diffusion to be positive recurrent. Okay. And choosing, so there are conditions for positive recurrence of a diffusion in terms of the speed and scale. So one-dimensional diffusion. So the conditions for recurrence and transience in terms of integrals due to, and these integrals are in terms of scale and speed of the diffusion. Certain integrals converge, then you have positive recurrence. It's actually an exercise in Karatza's and Shreve, which we found. Okay, so one can verify that. So this diffusion is actually positive recurrent. That means that starting from any point, expectation under X, huh? Same, symmetric. Sorry, the picture is not so symmetric around 0. Yeah. Okay. So it's positive recurrence. That means the starting from any X, the heating time of Y has a finite expectation for all XY. Okay. And in particular, it will start at A, it will hit B, okay, and then come back to A and continue this process. Okay. So there is a technical term for this. It's a regenerative process at A. Process is process XT is regenerative at A. Okay. It's basically the strong Markov property of the diffusion at the point A. Okay. So since the diffusion is strong Markov, it follows. Okay. So the definition is conditional expectation of theta tau of X conditioned on F tau is equal to PA of X. For every stopping time tau at which X tau is equal to A, for all stopping times, tau such that X tau is equal to A on tau finite. Okay, and this follows from the strong Markov property. So once what it basically says is that once you return to A, it starts off in an identical fashion. Okay. So it goes from here to B and then comes back. It keeps doing that. It oscillates infinitely often. Okay. Brownian motion does that, but Brownian motion is null recurrent and you don't have these. Okay. Next is transition path theory. So what we want to model now is to look at this diffusion and then look at the so-called transitions from that are happening. Okay, and that's a model. We model it using the crossing process, which I had studied long back in my PhD thesis. Okay, so this is the transition path process. ZT, we call it ZT, XT minus X sigma T, where sigma T is the last, it has a definition. So sigma T is the supremum S less than or equal to T, XS not in A. Okay. So sigma T's are not stopping times, they are random times. For each T, it's a random variable, but they're not stopping times. Okay. and ZT is this. Now ZT, I'll draw a picture which will tell you it tracks the behavior of X as X, this diffusion, crosses over from A to B and back. Okay, so let me okay, so suppose here's the A, B, and remember B is minus A, and the process starts off at A, okay, and it makes certain oscillations around A, and then at some point it goes over to B, does that, and then it keeps doing this infinitely many times. What does Z? So this is the XT process. What does ZT do? ZT tracks the behavior, but in a different interval. So ZT, so this is 0, B minus A, and minus B minus A. So in this interval, as XT goes into the interval, it reproduces that curve. So it's like this. But anything below A, it rubs out. Okay. So you get these excursions from A upwards. Okay. It rubs out all the excursions below A in this region. And then it captures this part. So you get a same trajectory here, reproduced here. And then at this point, it jumps to 0. Okay. So from here, it jumps to 0. And the excursions below B, it captures as, and then it does this part, and then the process continues. So ZT lives between minus B minus A and plus B minus A, and it jumps from B minus A to 0 when XT goes from A to B, and it jumps from 0 to minus B minus A when XT makes a down crossing from B to A. So it keeps tracking the crossings of X, but in the interval minus B minus A to plus B minus A. So this is the transition path process that we use. Okay. Yeah. And this part of the trajectory is what is recall that it was called the reactive trajectory. Okay, this portion. And the number of such reactive trajectories divided by T, that gives you the reaction rate. Okay. So the number of jumps of this process so for each such reactive trajectory, you have a jump when it finishes that, it has a jump from B minus A to 0. And the number of such jumps is the number of upcrossings. Okay. And therefore, basically, you're looking at, to compute the reaction rate, you're looking at the number of upcrossings in time T divided by T as T goes to infinity. UT is the Yeah. There are two processes actually going from the reactant side to the product, and it's also reversible. It can be reversible in the sense that the two rates, okay, going from reactants to product, okay, and coming back, these two can be different. In this case, we have chosen for simplicity, to have a symmetric. Sorry. Uh, yes, in some sense, yes. You'll see that little later also. That the potential U comes into play here. Okay. Uh, okay. This ZT. Okay, ZT is a transition path process. ZT satisfies a stochastic differential equation. Okay. So I think I'll rub this out, but it's good to keep this picture in mind of how ZT tracks the process X. Now ZT satisfies a stochastic differential equation, and that's as follows. So ZT, so the dZT nu of ZT dBT, dXT, sorry. So it's driven by the process X. L of ZT is 0. Now what is nu? Nu of X is the indicator of the set X. XT is our diffusion. Okay. And what is L? L is a process of finite. It's something like the local time, but there are additional terms because of these jumps. So you get the local times at A and B. Okay. Uh, uh, applied to the process ZT, yes. Yeah, thanks. Okay. So it's minus B minus A2 plus B minus. L of Z is, so as I said, it's like the local time, and it has this property that integral 0 to infinity indicator, I'll write it in terms of X, but this condition you can convert it into a condition on Z. Okay. The total variation. So this is like the condition in this cohort problem. Okay. That. And of course, Z0 is 0. It starts from 0 if X starts from A. So we'll assume all that. So remember, ZT has these jumps also, and the L, we have an explicit expression for L of Z. half LTA minus LTB minus B minus A UT minus DT, where UT and DT are the up crossings and down crossings, number of up crossings in 0 to T, number of up crossings in down crossings in 0 to T. They differ by plus or minus 1. So it's a bounded term, but it jumps at the endpoints where the crossings occur. So at a finitely many, so this has mass at these points. This is the continuous process of finite variation, local time, okay, of X. However, you can also describe it in terms of the local time of Z at 0. Okay, whenever X is in A, at A, Z is at 0. Okay, and similarly, when it is at B, Z is at 0. Okay, you can compute LTA and LTB or describe these two things in terms of the local time of Z at 0. All right, so this you can show that this solution of this equation with this L and this Z is a unique solution given X. One can show that. Okay, so this is the now coming to how do you actually compute this this limit ut by t? Okay, this is where the fact that it is regenerative, okay, comes in. One, we do that in this paper using two different methods. Okay, one is count the number of crossings in terms of the excursions of a crossing from A to B is an excursion of the process X starting at A of height B minus A. So you look at the number of excursions, okay, in an appropriate interval, not 0 to T, because that's the way the excursions are defined on the local time scale. Okay, so there's a little bit of care that has to be done in counting NT here in terms of the excursions of X from A. Okay, if you do that, the number of excursions is a Poisson point process, Poisson process basically. So NT by T you can compute using the law of large numbers. Only thing, it is on a different scale, time scale. Okay, so it will be something like this. So UT, if you want to write it in terms of the excursions from A, it will be NA 0 to T A. So this is the Poisson point process. Okay. On this, A is a set of excursions. In our case, A is the set of excursions of height B minus A starting at A, which gives you the number of up crossings in 0 to T. But that's not what we want, because the excursions are on the local time scale. So if you want 0 to T, UT, then actually you need to write it as LTA. And therefore UT by T is this by T. And if you want to take the limit, then what you do is NA LTA of A, where A is the set of excursions of height h, LTA into LTA divided by T. And therefore this factorizes, okay, into two limits. Okay, one, the first one, you can compute using the fact that NT is a Poisson process. NT by T, therefore, will go to the mean. NT by T will go to the mean. But in the mean, here is the excursion measure of A. So this will go to n of A, where A is the set of excursions of height B minus A. And LT by T, now here is where you use the fact that you have a regenerative process. Okay. And LT by T, as T goes to infinity, you will have expected value L tau 1 of A divided by expected A tau 1. But tau 1 is the time starting from A going to B, coming back to A. It's one cycle. Okay. So this is the expected local time in one cycle at A divided by EA of tau 1. Okay. How much time? Done? Okay. There's another way of counting this number NT by T, and that is using renewal theory. Okay. You can think of one cycle that is going from A to B and coming back to A as one renewal event. Okay. And you can apply the renewal theorem also to compute that number kappa, which is the reaction rate. Okay. So, I mean, this is roughly the results we have. Yeah, I'll stop here. Yeah. Oh.
So maybe we'll take some one or two quick questions. Yeah.
Describe the problem, it would seem like, I mean, if you are looking at the reaction and how many particles go, like what you explained in the, so you would have a large number of particles to the left of A, and each of these particles makes this journey. And so there is a distribution of particles on the left of A, let's say, and they are making this journey, and B is an absorb. Yeah, so they are all doing some diffusion to the left of A. And at some point they excurge and they go to B, and B is an absorbing boundary. And then you look at how many particles would have crossed this barrier, right? Yeah, correct. So how many particles would have crossed from? So that would that?
Actually, you model it in terms of a single particle. That's the way diffusions are. In actual practice, there are a number of particles. Okay. So you model it in terms of a single particle moving and making a number of crossings. Okay.
No, but I think his question is, once that particle goes to P, it can't come back to R. Right?
No, we allow it to come back to R.
I see.
But the rates can differ. In this example, the rates are symmetric. Okay. So it will seem as if there is no reaction, basically, or the equilibrium sort of is maintained. But the rates can be different. Okay. And so that will give you a difference in the net effect would be, particles going from R to P. That's how I understand it. I mean, huh?
Okay.
Yeah, in the model, of course, you can, once you go to P, you can come back. to R.
By the way, since the particle is starting from A, ut minus dt is either 1 or 0, right?
1 or, yeah, correct. 1 or 0.
Yeah, okay.
Yeah, it can't be minus 1.
Okay, okay.
Yeah.
Just that means the actual problem which you started was that the chemical reaction you were describing was the again I'm repeating the same thing, that wall the barrier, is it always can be transformed to the one dimensional thing, or it is you assume that it can be it can be okay, so okay.
There are certain So what I'm told is that there are certain systems where if you take a one-dimensional section, okay, so there are many coordinates and you fix all the other coordinate except one coordinate, okay, and look at the potential energy surface, then it will have that double well structure.
Other questions, I think we will take over the. So our next speaker is Dr. Imran Biswas. He is going to speak about obstacle problems for stochastic conservation laws, and not is not Levy, isn't it? Loewe-Stampakia inequality. Oh.
Okay, this is the right way of. Where is this? Yeah, so this. Oh no, this is this, and this is the. Okay. So these are fine. Okay. So I begin by thanking the organizers actually for this event. So Professor Ghosh actually is one of the very few individuals that I've looked up to all my life, and so it means a lot to me actually to speak on this day here. So of course, this the talk that I'm going to give here, it is a little bit actually off topic given today's sort of title of this symposium. But nonetheless, actually, you do have stochastic dynamics actually in place to talk about. So I'll take that. Okay. So this is about obstacle problem for stochastic conservation law. So and the particular sort of title actually here that I'm presenting, this is a joint work with Guy Vallet from France and a PhD student of his, Yassine Taharoui. So let me just lay down actually the plan here. So here, this is what we are roughly sort of going to discuss. What do you really mean by stochastic conservation laws? And then first, actually, I'll give a brief overview of the problem, a problem without obstacle, an overview first, and then we'll discuss, actually mention some of the differences, the work that has already been done. And then actually we'll basically, go on to actually discussing the problem, the entropy formulations and other things and so on. And then finally, we'll come down to the obstacle problem and formulation and, if possible, the well-posedness and so on. I will not get into actually any technicality here. I'm not going to present any of the proofs or any such thing. So that will actually sort of bore you quite a bit, I guess. If you're interested, you can let me know. Actually, I can send you the other details afterwards. Okay. So let me see. What is it that we are interested in? What do you really mean by stochastic conservation law? Okay. So those who are familiar with first order nonlinear PDEs, actually one of the first equations that you encounter is probably Burger's equation. Now Burger's equation actually is a very simple looking thing. The nonlinearity is actually pretty much, you see that, okay, fine, one can solve it and so on. But then it has a lot of fascinating features, including the solutions that You try to solve it and you figure out that actually the solutions are developing discontinuities and so on. So therefore, you have to actually deal with functions which are potentially solutions to a first order equations which may even be discontinuous. So therefore, this entire actually derivatives, that idea of derivatives actually it is sort of put upside down. So therefore, and here this equation actually this is, you can basically imagine that if you forget about what is there on the right hand side, that this is basically a modified version, a generalized version of the Burger's equation. That f actually, if the f is of the form like u square or something, then it will be the typical Burger's equation. So here, if the right hand is 0, actually it is called a conservation law, and there are some physics associated with it as to why it is called a conservation law. And if there is a right hand side, actually typically it will mean that it is not really conserved, but then there is some sort of balancing force field present and so on. But in mathematics, actually it is called as a nonlinear balance law. So that means it's a conservation with the source term. That is how it is known. Okay, so this is a simple looking first order equation, but then there are a lot of other features. It's not that easy to deal with. Okay, so here our interest, and that sort of our problem has been subjected to study for the last I think many decades, and still actually it is ongoing and so on. Nonetheless, here actually we are interested in a particular kind of right hand side, and that particular kind of right hand side actually where this right hand side represents some white noise. Okay, so here actually we will be mentioning specifically the Brownian type white noise. And what is that? So suppose this Brownian type white noise actually is given at least formally by this entity. Okay, so this will typically represent actually a drift which is represented by G, and then this another actually this multiplicative noise structure. The B in the notation here, it is typically a Wiener process. You just imagine that B is one-dimensional Brownian motion. You can actually take B to be cylindrical processes and things like that, but it is not really going to change the mathematics that much. Okay. Here, just to understand the problem, just imagine that this B is a Brownian motion. Now, if you notice, actually, I have written that this sort of derivative actually dB dt. Those who know Brownian motion, they'll know that actually the paths are of unbounded variation. Okay. And they are nowhere differentiable. So therefore, this entity dB dt actually doesn't make sense. Okay. But nonetheless, actually noise is a real thing, and then we sort of mathematically do study them. So how does one make sense of the whole thing? Is this okay? So instead of writing it as the derivative, actually we write the whole thing using the symbols of stochastic differentials. Now this equation, it is no longer involving these derivatives or anything. However, if the right hand side actually is 0, then basically you can just, it is equivalently could be made sense as a conservation law and so on, right? Now this right hand side, now what really happens is that all these dt's actually they are usual sort of made sense as integrals, and the last term actually this gt u dvt, this will be made sense as a stochastic integral, e2 integral. Okay, so therefore this entire problem now actually it is recast into this with this notation. This is now defined as a stochastic partial differential equation. Why partial? Because we do have these PD partial derivatives also present. Okay. So now, from my initial introduction, actually, we know that this even when the right hand side is 0, this equation is complicated enough, right? Now, if you add a noise, at least actually you're not really going to sort of soften the complications. It is actually, if at all, actually you have to sort of take into account of all of that. All right. So now here, so this is, so let me just sort of mention it. This is one of the things actually that sort of people have been looking at over the last sort of 2 decades or so now. And then there is another type which we are particularly interested is this. The right hand side, the noise structure, one can look beyond the Brownian noise, and one can actually look at this kind of compound Poisson noise. Okay, that is not really going to be today's talk. I'm just saying that it could one can also analyze actually equations of this type. Okay, or actually you can basically look at actually sort of possible Cadillac solutions. And so all that I'm saying is that the white noise structure actually it can be of many types. Okay, all right. So so typically in such situations you'll have to deal with solutions that are actually not only discontinuous in space but discontinuous in time as well. Okay, but I'll leave actually this part here. So now I'll just come down to this obstacle problem. The problem actually that is today's sort of topic for us is this. So suppose you have 2 obstacles. So you actually fix 2 levels. One is the fixed level 0, so that is constant. Another actually another psi bigger than or equal to 0. In our sort of overall context, actually, since we are dealing with SPDs, we'll allow this psi wherever possible actually to be a stochastic process. Okay, we need certain regularity assumptions and so on. I'll come to those things actually afterwards. But suppose these two levels are there, and then you want actually your state process or your solution to lie between these obstacles, right? So the first condition is that you should actually lie between 0 and psi. And then it should also satisfy this equation. Okay. Of course, the initial data actually should be satisfied. The initial conditions is a Cauchy problem, so the initial state or initial data should also be satisfying actually the obstacle. So with this, the question is that, I mean, without this obstacle, actually, this will be plain and simple. Let's say, stochastic PD, stochastic conservation law, and then you can sort of, think of getting a solution and so on. So therefore, here when you write this obstacle, actually, what it really means that it will be inside this and it will satisfy formally this equation. And one thing I must mention here, which is not there on the slide, is this, that it should satisfy this SPD away from the obstacle. So we really don't bother really what really happens at the obstacle. In other words, you actually, if it takes the value psi or 0, it's fine. We really don't look at the PD. But then suppose it is strict inequality holds. It is strictly between 0 and psi. At that point, actually, you want this entity to be satisfied. Now, then there is a problem. The problem is that here we are not exactly talking about partial derivatives anymore. Or actually, the right-hand side, these are all sort of separate notions and they're made sense as only Ito integrals, right? So when you say, when you say that this PD is satisfied away from the obstacle, it is not very clear as to what it means, okay? We'll come to that actually. Psi typically, let's say it is smooth enough so that if you apply the operator, then it should be like L2 actually should be able to sort of break it into positive and negative part and things like that. So those are this Lewis temperature thing actually sort of comes in at that place. Yeah. So typically what will happen is that in certain sort of under certain conditions on this G, you can choose this psi to be a constant, and then you want the solution to actually remain within these two constant barriers and so on. So such things are actually allowed. Okay. So therefore, here what really happens is that the solutions, like the way it is defined, they are defined to be certain predictive processes, and that is actually the case for problem without obstacle. And here, one good thing for problem without obstacle is the following: you really don't have this barrier constant anymore. You want just your PD to be satisfied. Thankfully, there is actually this entire extension of actually entropy solution framework available for stochastic PDs also. Okay, so what I'm trying to say is the following: you take the scalar conservation laws. There actually what really happens is that that solution might have discontinuities and so on. So then you have to typically go to the L1 framework, and that framework was developed by Khrushchev, and that is the entropy solution framework. And with that framework, actually, you can basically show the existence and uniqueness of entropy solutions. Entropy solutions are particular kind of weak solutions. So let me just put it this way. So we have had some exposure to viscosity solution theory, right? Yes. So this entropy solution, actually, this is somewhat related to the viscosity solution framework. How? As a matter of fact, this entire industry actually was started by Khrushchev, but somehow the credit goes to Pierre Lyons and actually Crandall. But Khrushchev is the person who actually started this viscous approximation, and then it is actually Kolmogorov's school, right? So what really happens is the following. So you, I can take certain liberty here, I think. So what really happens is that, so forget about everything. Suppose the right-hand side is 0, okay? So let me just go back to the, yeah, this one. So suppose here, instead of, let's say, finger. Yeah. Yes. So solution has to remain below psi. That is the barrier. U0 also, yes. Yeah. So that is the constraint problem actually. Okay. So here actually what really happens is the following. So I'm just trying to sort of give you the background as to what is it called actually vanishing viscosity and viscosity solution and all. So for this equation, this was originally actually Kolmogorov and Khrushchev, that school's approach was this, that on the right hand side, suppose it is 0, it is like a deterministic conservation law. And you know that like Barker's equation, you try to solve it by a method of characteristic, and you see that actually the solution typically is going to be discontinuous. But then what you notice is that in place of this 0, actually, if you add epsilon times Laplacian u, so that means a small diffusion operator, then the entire equation actually just becomes a sort of heat equation with a first order nonlinearity. So the entire dominant characteristic of the equation is actually manifested by the heat operator. In other words, you have a very nice solution here. You have a smooth solution, right? So now the idea is that if you let your epsilon go to 0, then so right hand side should become 0 actually potentially. Then what kind of solution that you are capturing? And this entire entropy solution actually sort of industry is developed to capture that if you let your epsilon tends to 0, then the typical solution that you capture actually that is actually referred to as the physically relevant solution and all, and that solution is unique actually satisfying these entropy inequalities and so on, right? So you have well posedness actually for that, and that is that. So what happens is the following. I'll just so come to that. So here, this is what I mean is this, that problem without obstacle actually it enjoys the entropy solution framework. And this entropy solution framework actually it was at least for multiplicative noise case for the stochastic problem was developed by David Nollert and Jin Feng. And then there were actually sort of many parallel approaches and so on, and there were actually like a couple of works actually of our own and so on. So nonetheless, this is not so old actually. This entropy formulation for stochastic conservation law, this kind of started actually around like 2007-8 at that sort of timeline. Now for the problem actually with obstacle, the trouble is the stochastic dynamics is just symbolic, right? You cannot really say that, okay, fine, at this point actually it is away from the obstacles, therefore all these partial derivatives actually they should take this value. No. That sort of an approach does not sort of make sense, okay? So therefore, what is going to be the appropriate formulation for the obstacle problem with the presence of noise, okay? And of course, with the formulation. Okay. Okay, all right. Yeah. So let me just briefly explain actually what this Kruskalov approach actually and why basically it works actually for the stochastic case as well. Okay. So the first thing is that let me just briefly explain why the entropy solution actually, why can you get uniqueness here? Okay. So suppose you have these two sort of dynamics here, and the right hand side it's the simplest form of actually stochastic conservation laws. All right. So you have like two solutions, and they're satisfying the same actually stochastic equation here. So you just for the timing you pretend that you have everything smooth, and you can actually carry out all the sort of derivations, chain rule, and everything. Then what happens is that you apply the Ito chain rule. You basically subtract this two equation. You apply Ito chain rule actually on this. You cannot do that. But for the timing, you just pretend that you can do. Then what really happens is that after actually some adjustment, this divergence term actually it will be basically could be written actually into the divergence of this term. Okay, that is just simple sort of algebra there. And then on the right hand side, those who know actually Ito formula, they'll immediately identify this sign of u minus v. This is just the derivative of actually this absolute value function, right? Okay. And so that is actually fine. I mean, but then this part should involve the second order derivative. Now, if you are actually looking at this absolute value function of u minus v, what is the second order derivative? The second order derivative is going to be the derivative of the sign, and which is Dirac delta. It's no longer a function anymore. Okay. And then you have this entire sort of other thing, the Ito correction term. What really happens is the following. And also, so therefore, first of all, you cannot really apply the Ito formula. Your equation does not have really the smoothness actually in order to apply this chain rule as is. And this is where the Kruskalov formulation sort of comes in. So there actually you have to go back to this viscous approximation, certainly adding a small diffusion operator, and then go there. So if you do that, if you sort of follow Kruskalov approach, what you'll get is that you will not really get an inequality here. You'll end up an approximation of the absolute value function, and then an inequality like this. But then that is also good. Why? If you just look at this one, what really happens is, so this is the divergence term. All right. So this is a conservative term. So if you integrate actually in the state variable, then the first term actually will survive. The second term, since the divergence of some entity, and integrating, that term will become 0. That is the conservation that is taking place. Then what you have is that if you integrate and then take the expectation, this other term, the stochastic integral term, that's a martingale. If you take the expectation, that should not really remain. That should vanish. Now becomes the Ito correction term. That is actually the problematic part. So if you just look at this, if you imagine that smooth approximation of the absolute value function, that smooth and convex approximation, then here instead of actually the derivative of the sign, you will get some smooth approximation. And that smooth approximation actually, it will basically be a singular term, but the singularity actually is going to be weaker. The singularity will be based on the line u equal to v. But that strength of the singularity is more or less like 1 by mod u minus v. Whereas if this sigma actually, if this is Lipschitz, then this is basically behaving like u minus v square. So in other words, actually this wins, right? So if everything goes well, from Kruskal's approach, if you're allowed to sort of approximate the absolute value function and carry out this E2 correction term actually should not appear in the end. And this is precisely what you have, okay? And that is what actually, David Nollert and Jin Feng's actually first paper is this. That so then what really happens is this. So then you look at this map. That here this equality is not there. This is less than equal to the second term. Actually, the contribution vanishes. The expectation of the first term of the right hand side actually that also vanishes. This other term actually it just disappears because this part actually the E2 correction, I mean the sigma u minus sigma v square that wins. Okay, so therefore, in other words, the differential actually of this term, or del t of this u minus v, this entity here, okay, that is negative. In other words, actually it has a direction. In other words, this is going to be this map t goes to this. It's a decreasing function of time. So therefore, at any time point actually we evaluate that should be less than equal to the value at time t equal to 0. And that is what actually what you have this classical L1 contraction principle, but in the stochastic case. So in other words, if you start with the same initial data, you should get actually the uniqueness. I mean, the solutions actually they'll be the same in the L1 sense. Okay. So therefore, and so therefore that is the plan. And based on actually this approach, many papers actually have been written, and it's still being written, I think. So these are actually some of the sort of things and so on. And it's there are other papers also actually which I could not simply cite, but these are sort of many things. But it started actually with this paper by Jin Feng and David Nollert. Largely, there were papers before that, but they didn't really sort of do this entropy formulation thing actually that robustly. Okay. In any case, so now actually, so let us just go back to this formal approach to a more rigorous sort of approach, right? So what is it that I was meaning actually? So you just look at this viscous perturbation of your equation. I'm sort of looking at the simple form here. All right. So all of the source terms and everything actually they are sort of gone. And then what you have is this equation actually it's a stochastic heat equation, the first order perturbation, right? So even if it's an SPD or so on, these lower order actually perturbations, they will not disturb the regularity. So you can show that actually you have a strong solution. Okay, of course you have to start with a sort of regular enough initial data and so on, but those things you can do and can claim that this is basically a stochastic heat equation of a smooth solution. Now you go for something called this convex entropy pair. What this convex entropy pair is that zeta is actually like, let's say it has certain relations between, it satisfies certain relation between beta and f, and this beta actually it is typically a smooth approximation of the absolute value function, and it's a convex approximation. So there are certain signs and so on, right? So what really happens is that since it has a smooth solution, you can actually apply your retrieval formula to this entire entity, and then this is the inequality that you are going to end up with. This is the equality that you are going to end up with. So this will require actually some sort of let's say simplifications and other things, but these the red terms. These red terms are because of the presence of noise. Okay, so this is the first red term actually is the stochastic integral. The second is the E2 correction and so on, right? So those terms actually they are going to be surviving there. Now, what really happens is that the last term actually this beta double prime, and then you have this other negative term, right? So this beta is chosen to be convex. Beta double prime is non-negative. So therefore, that other term actually, though it is a very bad term, it is basically epsilon times grad actually u square and so on. That will be a singular term, but it has a sign. So if you neglect the sign, this equality actually will become less than equal to. Okay. Yeah. So and then what really happens is that this Laplacian times this term, as you can see, actually, if you integrate this whole term, this Laplacian actually that could be transferred onto the test function. The other term becomes free. So if you are actually multiplying the equation with a smooth test function, then in the limit, if you have stable estimates and so on, in the limit, the first term actually of the third one, okay, it should not really exist, right? Because the derivative is on the test function and so on. And this motivates the entropy inequalities. In this case, actually, this is going to be our entropy inequality. Okay, so basically, or formally, actually, if you want to define the entropy solution, this is going to be the solution. All right. So what is this? First of all, your solutions actually, at least they need to be integrable. They need to satisfy certain moment conditions. So these are all sort of standard. And on top of that, actually, for every convex bounded beta, you can actually allow certain growth and so on, depending on what kind of moment estimate you have actually for your solution. But it's enough actually if you start with bounded. Okay, and then these inequalities actually they are satisfied for every choice of the test function and everything actually almost surely. Okay, so the terms actually that are described in red, these are the new ones that you get as a result of actually the noise. Okay, so if you have that, you can adopt actually like Kruskal's approach by smooth entropy, and I have described that part. So then this will validate the classical Elon contraction principle. By the way, that will give you the uniqueness, but the existence actually is much more sort of subtle. Why? Because for these equations, as you can see, the gradient estimate actually blows up. So you cannot really use any compact embedding argument or anything, and the equation is nonlinear. So just having pure sort of LP type bounds, all that you can get is weak convergence. A nonlinear equation, weak convergence, it doesn't really go well, right? So what really happens in that case, there are many ways of doing that. And one of the way actually is you treat actually your, these LP bounds for the solutions, you treat your solutions as Young measures, then you get actually tightness of the sequence, you have subsequential convergence, but limit as the Young measure. Then you use again Kruskal's mechanism and show that the Young measure is actually represented by a function. And that is going to be your function. So it's easier said than done. You have to do a lot of sort of jugglery there. But nonetheless, ultimately it will work. So basically, this existence part actually, I guess this, this Young measure that is really general and so on. If I recall correctly, the first result for one dimension, the first result was that you assume that your initial data is BV. And then you have this uniform BV estimate. The BV is compactly embedded in L1. Then you have this L1 convergence. If the initial data is not BV, then you use this, what is it called? Actually, this compensated compactness and other things and so on. So this, basically a lot of this one actually is this existence via Young measure. It basically uses actually the intrinsic uniqueness of the equation and actually these other conservative actually, structures. And then it claims that the Young measure limit is actually a function, and that is your unique entropy solution. So here, what I'm trying to say is the following: uniqueness is a bit, existence actually is a little bit involved. Okay, but nonetheless, you can get, and here, so, oh no, so this is, I think, okay. So what I wanted to show you is the following. So now, as per the existing theory, what really happens is that you have this L1 contraction, everything is nice and so on, but then. This is actually another sort of, I'm going to talk about actually a piece of our work, which I did with us to PhD student Shaibal and another collaborators. And this is basically about like, can we really sort of have a slightly different take? Can we really actually better the estimates and so on, okay? So can we really have some path-based actually, things? I'll just briefly mention that. So this was the goal, that we know that this map, actually this is decreasing function of T. So this is the classical actually L1 contraction. It ascertains actually uniqueness and so on. But how about actually this entity that you basically take this L1 difference, but over the entire path, and then you look at the expected value, right? So this is definitely a much stronger quantity than this. And you are not really, so basically this is depending on the entire path. So there cannot be any L1 contraction thing per se. So here, what really happens is that we look back actually the formal calculations, and we see that you have basically, these other red two terms, they could be ignored. And then for every path, what you have, basically this stochastic integral term. So here you cannot take the expectation. You have to take the supremum before taking the expectation. But thankfully, what really happens is this right-hand side, actually the red term, actually it's a martingale. So you can take the supremum there. You can apply BDG. And after the BDG, actually you can control that with a sort of combination of Gronall and so on. You can get a real estimate of this entity, okay? Yes. So basically, this is the part actually that, so suppose if you want to sort of formalize actually our approach, so we do this vanishing viscosity. First, we get this uniform actually estimate on the entire path of the gradient. Then basically what happens is that here actually we try to do this L1 contraction actually for the viscous approximation itself, and we end up actually this sort of inequality in here. So as you can see, if these two terms actually, they could be somehow actually sort of led to zero, which could be typically the case if you regularize actually the initial data suitably, then you will basically get the desired estimate, okay? And then, and also actually it also gives the compactness actually of the sequence. In fact, it sort of gives that in this entire space, it is Cauchy. So what really happens is that there are many things that you're improving here. You're actually showing that the solutions, they have continuous sample paths with probability 1. That's the first thing. Secondly, you have this, this sort of estimate. So these are essentially actually well-posedness, but on a much stronger platform, okay? And this is basically the result that I just wanted to mention. This is not really the obstacle problem. This is essentially our students' actually PhD thesis last year, and but then I'll come to the obstacle problem now. Okay. So for the obstacle problem, let us just go for some of these notations here. So what is this notation here? It is so first of all, this SPD, it is all evolving. So you need a stochastic basis for that. So what is that? A stochastic basis, actually, it's a filtered probability space that is satisfying the standard hypothesis and so on. Okay. So basically, beyond that, actually, we really don't say much about these things. I mean, whatever calculations that we are going to do, if it is, it's all going to be allowed actually in a space like this. Okay. Then you have this V actually is the Hilbert space H1. So it's basically the functions actually which whose derivatives are L2. Okay. And then H is equal to the L2 space, and then this omega t, this is the sort of the Cartesian product of the sample space and actually the time interval. And then this NW2, this space actually, this is the Hilbert space of predictable processes actually from L2. So basically they have to satisfy this additional measurability actually criteria. That means they're predictable and so on. So in any case, so predictable means actually like, they should be pretty close to actually late continuous processes and so on. Okay. So now here, so let us just go to the viscous problem for the viscous perturbation for the obstacle problem. So what is the viscous problem? So we are a little bit lost there. So here actually what we do is the following. Here the problem is this. Again, you have the same obstacles. Here the problem is to find some mu epsilon such that they'll be remaining within the obstacle, but then at the same time actually they'll be satisfying this stochastic PD now, which is a parabolic one, away from the obstacle. Okay. So if we can actually give a sense to this problem somehow, then actually we can pass to the limit and we can try to make sense of our stochastic conservation law with obstacle actually, right? So here, what we do is the following. So let us just define this. So what is this? This is basically just restatement of this operator actually in this sense. So what is this? This A is taking value actually in H-1 here. Okay. So all that we are doing is basically this is we are just multiplying this equation, the main operators actually with our test function W, and then just transferring the derivatives and so on. This is fairly standard actually things in PDs. Okay. So now with this notation, actually let us just come to this. So as to why this is the definition and all, actually we'll see. So now we can recast actually this obstacle problem as follows. What is this? You find this triplet. So E epsilon is typically the solution that you're looking at. Then these other two quantities, K epsilon 1 and K epsilon 2, all are actually predictable stochastic processes such that it will satisfy this stochastic differential equation. Okay. So now there is no obstacle actually per se here. It is satisfied at every point. Okay. So this is this omega t actually cross RD, and the initial data is also satisfied. And then first of all, U epsilon is required to be inside the obstacle. This K epsilon actually, that is nothing but it's the difference of K epsilon 1 and K epsilon 2. And then another thing is that you see this K epsilon, it should be K epsilon 1 first. K epsilon 1, the product with epsilon minus psi is 0. So that means what? K epsilon 1, it has only support actually when U epsilon actually is hitting the obstacle phi. K epsilon 2 at the same time, yeah. It's not really a local time per se. It is, let's say, more like actually if it hits that, it is, we really don't sort of, care about the equation actually. Yeah. So yeah, it is, you can somewhat, some sort, say it actually a little bit like that, I guess. But this is more like, this is how things are done for deterministic obstacle problem, right? Okay. So what you do is that this term K epsilon actually, this is acting a little bit like the Lagrange multiplier, if you like. Okay. So this is keeping the constraint actually somewhat within the range. All right. So in other words, if E epsilon actually is strictly less than psi and bigger than 0, then this K epsilon actually it will be 0 and then your dynamics is satisfied, right? And if they hit the obstacle actually at that time, you really don't care actually what really happens. Okay. So in any case, they're all positive. So the equation has certain directions and so on. So therefore, this is going to be the interpretation actually of the viscous obstacle problem in our case. So here, the presence of the obstacle is kind of encoded actually in the presence of this term K epsilon, which behaves like a Lagrange multiplier here. Okay. So this is the typical role of the Lagrange multiplier, right? It sort of keeps alive the constraints. All right. So with this actually, so now the question is that okay, fine, we have a problem. Now can we get like well-posedness for this? Okay. As it turns out, okay, so this is another sort of all the admissible actually test functions and solutions and so on. They have to be remaining with that. Okay. So the definition of the solution would be actually, all the other conditions that we have sort of started, and then the stochastic dynamics. It will now, as you can probably remember, that A actually was defined as an operator actually, which takes value in h minus 1. So this entire dynamics actually, when defining as stochastic integral, actually it has to be interpreted in h minus 1. Okay. In any case, it's a good Hilbert things actually do work there, and once you do that, then this dynamics actually could be given a meaning, and basically all the other conditions, the last line actually, these are basically equivalent to saying that this should also be k epsilon 1 minus epsilon minus psi actually is equal to 0. They're equivalent. Okay, so you are basically casting everything actually in the form of test functions now. Okay. So with this definition actually for solution, the question is that do we have well-posedness? As it turns out, we have. So what we do is the following. You go for this penalization method, and this is actually quite similar to what you would do for deterministic equations. Okay, so that way actually it is not really very different. So as you can see, this is actually you take an operator and you perturb it by these singular terms, this penalization actually factors. So what is this? This is 1 by kappa, and kappa is a very small parameter, and this is uk minus actually psi plus. So therefore, for any possibility, so suppose at any point actually the equation sort of travels above the obstacle. So that means uk minus psi is positive. Then it is very severely punished actually. This term actually is made singular, right? So these singular terms, if the equations are well behaved, then it will force actually the solution to lie within this range actually from 0 to 5. So both are actually the same. More than that, what really happens is that all these actually penalization terms are monotone. So since they're monotone, actually, you can just multiply, them, and you can just apply energy method and so on. These monotone terms, they will not really have actually any effect in the a priori estimates of, for the solutions and so on. So where this is a very good, nice approximation to have. What is the good part? The good part is that there is no other things actually. This is just a simple sort of, parabolic. And here, what you say actually, this is let's say 0th order actually nonlinearity here. They are all Lipschitz. So you have existence smooth solution and everything. So here the UK actually, they will also depend on epsilon. It exists actually as a smooth solution, right? So now here, so therefore, this well-posedness actually for this equation, this will follow from a scalar equation, and it's fairly standard. Okay. So now what really happens is that, so these are some of the things actually which you can easily prove that this sequence UK now, it is bounded in L2. Then this you apply this operator, and this is going to be actually bounded in L2 with value in h minus 1. And then even the other actually sort of what is it that I'm sort of writing here? Anyway, so I guess okay. So this is I'll come to that actually in a while. Yeah. So what really happens is let me see. I think yeah. So not only that, this UK actually this is going to be a Cauchy sequence. Okay. Cauchy sequence in L2. So therefore, actually, you do have a limit. So it's a very strong sort of thing. So that we can pass to the limit k tends to actually 0 in this space, which is a fairly nice space. It's not really H1 but L2, and then after that you can go back and so we have a sort of nice framework. You have a solution. More than that, actually, what I let me see if I have mentioned it here. No, this is I think I have forgotten. So you just look at this other penalization term. This 1 by k. I think I missed it here. So 1 by k, UK minus 5 plus this entire entity, this is actually going to be bounded in L2. Now, it is bounded, and that requires quite a bit. So because if you multiply it with the test function here, you will really not get that this entire entity is bounded by L2. And in order to prove that actually that is bounded, this is where this Levy-Stampachet type inequalities will come handy. Okay, first establish that, and from there actually you can just go for the standard sort of estimates, and you will get that. What really happens is that since actually these two terms, the penalization terms, both are going to be bounded in L2. Your sequence is a Cauchy sequence in here, so therefore you can pass to the limit. If you actually want to pass to the limit in the equation, that is a bit of a problem. Only bound that you have is in L2, but then for L2 actually you have weak limits, so you get the weak limit. Now for the weak limit, actually you basically show that there is this monotonicity characterization that are still maintained. Okay, so if you do that, then what really happens is the following. You will basically end up actually an equation of this type. What is this? You will have this U epsilon, which is going to be the limit of these UKs, and then you have this. Oh no, there should be 2 here. It's square integrable and so on. So this NW actually it should be 2 here. Okay, so this guy, this is typically going to be the weak limit of actually all the penalization terms. And then they are going to satisfy this stochastic PD. And what is this? Furthermore, actually what you have is that these are now just L2 functions, but these L2 functions actually they'll behave this way. What is this? They are going to be supported actually on the set actually where U epsilon, it does not hit the obstacle. Okay. So basically within the obstacle, actually, if it is strictly within the obstacle, this Lagrange multiplier term, which is gamma epsilon, that is 0. Okay. So this is going to be interpretation actually of your let's say obstacle problem actually in the viscous case now. All right. So therefore now since we have this format here, and then along with this actually what really happens is that once you have that, and that requires actually these Lewis temperature type inequalities and some degree of trickery and so on. And then you can basically go for the fair sort of the energy methods and all, and then use the monotonicity of the Lagrange multiplier term to come up with these estimates. Okay. So these estimates then actually typically what happens is that these estimates, they're not really good estimates, These estimates actually they're just L2 type estimates. Okay. I mean you really don't have this compact embedding or anything, but ideally remember we started with conservation laws, right? With noise. So ultimately we need to actually pass to the limit this epsilon going to 0. These estimates are not really very good for that. But here what really happens is that we at least have this viscous dynamics. Although there is a Lagrange multiplier term here, what really happens is that we can still apply the Ito formula, the chain rule, and we can hope to get an entropy formulation. And we do get an entropy formulation. Then what really happens is that so therefore now what will happen is that so we are looking at potential limit of this triplet, right? So these are the Lagrange multiplier terms, E epsilon, actually gamma epsilon 1, gamma epsilon 2. So therefore any potential solution that should have potentially 3 components, right? So one is for the solution itself, another 2 actually will signify the Lagrange multiplier like term that will control the obstacle. And so therefore the obstacle actually, as I said, it is going to be somewhat regulated by this Lagrange multiplier term, right? So now, of course, so therefore, based on this, actually, we can define the entropy solutions. And then what will happen is this, that any entropy solution, potential limit, it will all have to satisfy actually all those, entities, they were satisfying for epsilon. And you can actually show that pretty easily, right? But here, again, the estimates that you have, they're just LP type estimates. You don't have a convergence subsequence here, okay? So there, what we do is the following. Then what really happens is that you just look at the entropy formulation. The entropy formulation now actually it will have an additional term that will correspond to the Lagrange multiplier term, which will be like this. Thankfully, what happens is that this Lagrange multiplier term gamma, it will have certain monotonicity property again inbuilt. So therefore, this term actually, even in the L1 framework, if you do a Kruskov, you can actually control it. It will require some effort, but you can do it nonetheless. And once you do that, actually, then you can say that okay, fine. I mean, I'm able to actually carry out Kruskov's thing. And then I can at least prove the uniqueness, that if there is an entropy solution, at least this is unique. So once you have uniqueness, then you can actually do it just like the scalar equation. And then you hope to carry out actually that, okay, fine, I have these L2 estimates. I can actually claim this sequence again as a tight sequence as, and claim convergence as Young measures. And then from there, actually, we can recover. So what really happens is that the monotonicity of this term actually like saves the day. And then we can exactly do like the scalar equation. We can actually claim that the Young measure limit actually of these epsilons, that will be the unique entropy solution of the obstacle problem. So therefore, we can actually have, yeah. Yes. So I think I have just mentioned actually all of it. So therefore, actually what will happen is that once actually you have basically set out this, you have, let's say, finalized actually this obstacle problem actually formulation via Lagrange multiplier, it basically allows you to sort of treat the entire problem as a parabolic stochastic, stochastic differential, stochastic PDE, and then you have all the other tools actually at hand, and you can actually claim well-posedness for the problem. I'll stop here.
Questions. any questions from actually the online participants? Okay, so
Young measure includes direct measures and all that.
No, you see, Young measure is basically parameterized family of probability measure. Okay? So yes, I mean, if you say that actually it's all does include. The point is that Young measure is there. Now the Young measure is, yeah. So you,
Yes, it does.
yeah, it does. Yeah. So it could be any probability measure for that matter. It's just a parameterized family of probability measures. Now here in the specific situations, that probability measures they'll be represented by actually a direct delta supported at a certain function. That function is going to be. So yes, as a matter of fact, that is what we are proving in the end. The uniqueness of the equation forces the Young measure, the limit Young measure, to be a parameterized family of Dirac masses.
any other question? If not, both this one.
So yeah, we'll have a coffee break and reassemble at 4 for the reminiscences session.
50 minutes.